So thanks everybody. Thanks Ben for this joining this and giving this talk. Let me first introduce Ben. And Ben is a developer technology engineer at NVIDIA, where he focuses on HPC workloads and AI enablement. The recent work includes developing an AI agent to automate most of the effort required to port large Fortran HPC codes to GPUs. Previously, Ben was a scientist at Los Alamos National Laboratory, where he contributed to the Jayenne radiation transport code and the Parthenon, the performance portable multiphysics framework. He also led an LDRD Directed Research project to numerically model giant planet formation. Ben received a PhD in astronomy from the University of Illinois at Urbana-Champaign in 2018, where he wrote a hybrid parallelism relativistic radiation magnetohydrodynamics code to simulate black holes. And today he will give us a talk about the Acceleragent, an agentic AI approach for porting HPC codebase to GPUs. The floor is yours, Ben.
Okay. Thanks for the introduction. Thanks so much for having me here. So I had a question about timing. Is this a 45-minute window, talk plus questions?
Yeah, 45 minutes, including questions, ideally.
Okay. All right. I'll stick to that. I brought a few too many slides, but I'll skip through a couple. So I'm happy to be here today. So like you said, I previously was at Los Alamos Lab, and I spent a while working on the Parthenon code was something I worked on. So that's built on top of Kokkos. So I've been using Kokkos for years to really good effect. So happy to be talking with you all today. And I think Parthenon was presented here a couple months ago, actually. So let me. Okay, so yeah, today I'll be talking about some more recent work I've done. Basically, we're calling it Project Acceleration, a project designed to sort of see what's possible with AI models today in terms of getting at least first cut end-to-end GPU ports of scientific codes, speeding up that process. And so historically, that's been a challenge, an expensive initial cost to taking a CPU code to GPU, and this has been a big motivator for performance portability frameworks as well. When you have a million-line code, a complete rewrite's very expensive, and so in the past year, 2 years, large language models I think have become quite good at writing at least small bits of code that are correct and well written, I think, from a programmer perspective. I'd say since sort of the advent of models with extended thinking, so sort of DeepSeek V1 onwards, GPT-5, Claude Sonnet 4.5, and later, these models are really quite strong at writing good code that's can still have bugs, but is close to the right thing. The challenge is that a small snippet of almost right code is not the same thing as a complete rewrite of a very large code base with many production requirements. So and a typical LLM will have maybe 1 million tokens worth of context, which is some number of thousands of lines of code, much less than 1 million line code base. And a single turn of an LLM can't take even its whole context window of code and produce correct GP ported code in a single response. And in the past couple months especially, this landscape has really been changing pretty fast because general purpose coding agents like Cursor and Claude Code are starting to close that gap in a general way. So an agent is like a wrapper for an LLM, essentially, where it repeatedly prompts the LLM with some continuous stream of thought and can get answers back, think about where it is, call tools, get more information, and sort of scale out its run as long as it needs to solve larger tasks. But even for the best agents, I don't think that simple prompting, like just port this code, do it, don't bother me with any details, that's not really sufficient to, I think, get a useful result out in terms of a ported production code. So we started this work before the general purpose agents, and I think that we in the field and everyone are sort of converging on the same ideas. But this is sort of the spec of what we tried to do is, can we sort of use the human workflow to find to inform how we interleave LLM calls to use many LLM calls, each creating sort of a small amount of pretty good code to get something that's really, a correct production ported code. Um, that's kind of what agents do in general. But the idea is that you have these really useful individual LLM responses. You want to assemble them into something that, obeys numerous constraints and has the right large scale behavior that you want. Um, I think one of the key challenges with production HPC codes is that you have to maintain correctness defined by the users. So there could be hundreds of tests, results need to be stable across versions. And the thing LLMs can't do is truly measure the correctness of of the code they're generating during a response. So correctness is really measured by tool calls and not AI itself. But it in computer science, we already have lots of tools for measuring errors in code, right? So there's compiler errors, there's runtime tests. These all produce, useful information we've all used for a long time to write our own correct code. And so I think the way to bring AI into alignment with, production code engineering is to expose these tool results to the AI itself. So the AI will write some code, it's good, not perfect, there'll be some compiler errors. You could send those errors directly back to the AI and have it, have it fix those errors. So this is becoming, a standard way to use AI, but I think it's sort of one of the key pieces in bringing, getting long-running AI working on HPC codes. So we sort of have these two kinds of inference that we're doing in this project. We're writing new code and then we're fixing those errors and integrating that new code into the original code base. And these are, I think, both crucial parts to really effective long-running AI use and code porting. So the simplest approach, the first thing I ever tried thinking about AI code porting is just you take some legacy code with many files, you pass the files one by one into ChatGPT, they all get translated into some language, but the resulting set of translated files doesn't compile into working code, and the individual files aren't aligned with each other. So you you get all these new files, you type build, and it's just, an infinite sea of errors that really can't be fixed because the result of having sort of probabilistic rewrites of each individual file, that aggregate is too far away from a real ported code to be useful. Or to be correctable by human or an AI. So this is kind of uh, there's not really a good way to proceed from that point. So the model we use is, again, really just inspired by human workflows, where if you were going to port a code, you wouldn't sit down and just type for days and days transcribing code and then hit compile at the end of that and it doesn't work, and then what? The way we develop software is sort of taking incremental steps and making sure they're correct, continuously aligning to the requirements of the program, and then sort of stacking these steps up to sort of navigate the space from an original CPU code to a ported code. And this is kind of what we've seen generically working with AI as part of this project, is that there's like a radius of convergence essentially for AIs to fix their own mistakes such that they are get a correct result that's aligned with user requirements. And so what a sufficiently small step is depends on the model, depends on the code, depends on the the user requirements, and that's something that the human user, I think, needs to be involved in. But we've tried to define a set of small steps that sort of are generically applicable to porting HPC codes, and that's part of what this project is figuring out what those steps are and kind of sharing that knowledge, sharing demonstrations too that it appears to work. So this is the building block of one of these steps, and I think this is a pretty common pattern in AI. In AI software engineering now. So we take some working code, the LLM's allowed to make some incremental change according to some request, like convert this function into a kernel. And then rather than just accepting that, that goes into the verification loop where often most of the work is actually done. So we've defined some way to build and run the code to determine whether that's correct or not, just like like a Git CI suite. So if that returns success, then we can assume the code is correct and we keep going to the next step. And if it's not, then we take those errors and send them back to the AI, let them fix them, and rerun the tests. And we block until this step is actually until verification succeeded, because it's not really recoverable to continue accumulating errors as you proceed with software engineering. So the fallback is not to accept some errors and keep going, but rather to, if the AI decides that if the AI tries too many times and can't fix some verification error, we fall back to the user and say, look, something's wrong. I can't fix it. The human needs to take over. And maybe there's some logical flaw in the particular verification being requested or something, but the space of possible failures is very large, and so this is ultimately the user responsibility. So in a fully autonomous workflow, the AI never hits the user, the code gets ported incrementally and everything's fine. But there's sort of always, I think we've seen that there needs to always be a fail-safe where the user gets roped in when something is just not right, when the AI feels like it's not able to properly interpret the request, properly respond to it. So then I think one of the big questions is just how do you chunk up a code porting project generically in a way that makes these small enough tasks that the AI is likely to succeed on its own. And the approach that we picked is something that we've used in NVIDIA DevTech for a while, especially for porting Fortran HPC codes to CUDA, where so this top row is like a schematic of a Fortran HPC code. So you initialize some data, do stencil operations with data parallelism, communication output. But most of the work's done in the stencil operations here. And the step-by-step approach to doing this is to leave the original code as it is, but for each of these data parallel regions, separately shim in this case, Fortran to C interoperability layers, and then initialize GPU data as necessary and run on the kernel and go back to the host. So this is a scalable way to kind of rewrite a code piece by piece, and at least get working GPU kernels on the device running in the original code, and you're left with both the original CPU code and the resulting GPU code, and it could be switched, in our case, with a compile time switch. Looking at this diagram, using this naively, you immediately get very poor end-to-end performance, because doing CUDA mallocs prior to launching every kernel is sort of disastrous, right? So there are two ways to approach that. One would be to take all these the CUDA mallocs in front of each kernel and sort of move them up to a data initialization layer. But instead, we've found good success just leveraging managed memory approaches, where it's really on the runtime to detect page faults and move memory as necessary. The problem of collecting all memory copies into a centralized location on a code base scale is actually kind of difficult for AIs, because it requires large scale knowledge of the code, whereas this approach really isolates a function and writes a GPU kernel and gets it working in the larger code without hopefully having to traverse too much of the code. And the other advantage of the region-based approach is you can sort of quickly assemble standalone unit tests for each kernel you create. So we have the original CPU code, we have the GPU code, and they both have the same function signature. So it's easy to write a standalone test program. You ask the AI to initialize some reasonable data that should test the function. You can ask how detailed you want it to pursue edge cases. In some sense, you're relying on the AI here to do the right thing. But I've found, for the purposes of getting things mostly right, beyond specific user requirements, the AI does a pretty good job of figuring out initial data and what to compare. So the AI can write this whole test program for you, initialize data, run both functions, compare the results to some tolerance that's appropriate. And this in particular is very useful for having the AI fix its own runtime errors. So a GPU seg fault in the context of a very large code is difficult to find and debug. But if you can fix those memory errors in standalone tests before trying to verify the whole end-to-end program is correct, that really accelerates how fast the AI is able uh, to fix its own bugs. And I think this is something that we've seen with human dev techs for a long time. These standalone tests really speed things up. So here's kind of a schematic of how we assemble all this into tasks for the AI. And so this diagram is actually deprecated now because this is for a top level Python program that sort of steps LLMs through each task, uses F strings to write prompts and sends them to an API for individual completions. And just in the past month or two, we've started transitioning to a purely skill-based approach for general coding agents. I'll talk about that in a second, but the skill-based approach essentially follows this workflow, but some of the decorations like whether we're using an AI agent or an AI model for individual steps, that's sort of not meaningful anymore. But the basic idea is you start with the CPU code, you give it to the agent. So the input to a project acceleration tool is like the path to a code base. The agent first kind of reads through the code, understands what it's doing, where things are. Then it does some initial work to kind of prepare for GPU porting, like make sure you have the right GPU tools, kind of wires them into the build system. Maybe it does some extra language specific work like isolating domain programs so you can share global variables with your standalone test programs. Maybe you wire in some prepackaged unified memory code we have for specific languages. So then it gets ready to build the code for GPUs, and then it plans the port. So this is an important part of kind of taking the user's attention, requiring less attention from the user, where we have the AI read through the code, look for data parallelism in the code, places, and kind of find the right level at the program where we should be launching compute kernels. And the AI is sort of for the lifetime of this project really been doing a good job of finding that, I think. So it tends to be pretty predictable in where it marks functions for translation, and it does a pretty good job of finding the right places to do that translation work. And it does a good job of not tagging functions that call other functions, such that you would have kernels launching kernels, that kind of thing. But it basically gives you a plan of which functions it's going to start looking at to do porting, and then it sends this plan to the user and says, are you happy with this? And the user could say, well, you forgot about this other function, or I don't need you to put the initialization routines on GPU. And you go back and forth with the AI until you get this plan of a set of functions to port. And once you have that, there's some refactoring operations that we can do to sort of move data parallelism up and down function levels to kind of get it exposed in the right place. This is kind of, I think, the most active area of research for us now, because in principle, refactors can cover very large swaths of code, and how we do that's very different for a Python program versus an agent skill. But that's kind of the frontier of this work now, is really substantial refactors of code to get data parallelism in the right place, especially in the context of like porting object-oriented CPU codes. But assuming the data parallelism is in the right place, then we just port functions one by one. So we start by writing a test scaffold, and then if we're going from, say, Fortran to Kokkos, we'll translate the Fortran to C++. We'll test that the C++ and the Fortran give the same answer. Then we'll translate the C++ to Kokkos, test that the Fortran and Kokkos are giving the same answer, and then integrate that translated function back into the original code base and make sure the whole code works and still gives the right answers. And that the result is the ported code. So, like I just said, we originally wrote this as sort of a command line program in Python that would assemble prompts and send them to AI APIs and get JSON formatted responses back. And we had all this logic to, basically implement a full coding agent harness. And I think in the sort of more than a year ago, it was important to do that because the models weren't good enough at following long to-do lists themselves. Like you really had to enforce a sequence of work to the AI. And that's sort of not true anymore. Claude Opus 4.8, for example, is I think extremely good at following a detailed set of instructions and not only sort of moving through them the right way, but kind of reliably, running tests when it's supposed to make sure it doesn't get out of sync, or make sure it doesn't accumulate too many errors. Oh, sorry, I don't know what happened there. Okay. Yeah, so, and the other problem with using a deterministic orchestrator is that it really was not robust against, the many patterns you see in a general large HPC code. There's sort of every new code we tried on this, there was always some edge case we hadn't foreseen in that kind of broke the deterministic control flow. And so a month or two ago, we tried just an agent skill version of this Python workflow, where instead of the Python logic, dictating how we move through this flow graph of operations, we basically just type that flow graph out in plain text to give it to the AI and say, look, here's what you need to do. And depending on the language, the skill also contains some information on how to write good GPU kernels for a specific language. And the other thing that we do now is we sort of have the agent run Nsight Systems, which is a program scale profiler from NVIDIA, which kind of shows you, a timeline of your program, where wall time is and which parts of the code are responsible for that. And the agent now uses that to help plan its porting efforts, and it can iterate over those system level profiles to see where white space is on the GPU and figure out what else it needs to be porting to get rid of that or get rid of memory motion issues. And so we're kind of pivoting to this now because it just seems to be more effective than us trying to write our own Claude code. Essentially, there sort of seems to be no strong reason to do that anymore. And as the general coding agents get better, the skill version improves along with those. So Project Acceleragent is sort of it's kind of our investigation into what the best workflow is for porting CPU codes to GPUs with AI, to sort of remove as much of the time developers have to spend as possible getting that first cut port of getting a CPU code working on the GPU, not necessarily with perfect performance or getting every last bit of code on the GPU, but basically doing most of that just typing work of getting everything rewritten. So, designs a plan, does the work, fixes bugs, and the goal is to cut, 90% of the time to first solution off. So the humans should still be around watching the AI, but the hope is the AI is mostly running, by itself. Yeah, and I think we're trying to demonstrate too that ambitious goals like that are sort of reasonable with AI where it is today. I think we want to demonstrate this code was ported, it took this much time, and communicate that. So Project Acceleragent is not like a product or a superhuman intelligence that gives the perfect GPU port with no effort. I don't think AI models are there yet, and I think it doesn't make sense to take humans that much out of the loop either. And it also doesn't sort of re-architect algorithms themselves. So CPU codes will have algorithms that are just kind of fundamentally not suited to GPUs, and Acceleragent will port those algorithms faithfully and get bad GPU performance. And I think when it comes to changing algorithms, that's a place where the user needs to be involved essentially to make decisions. And Project Acceleragent also is not linked to any specific LLM or any specific coding agent. So it's designed to sit always kind of above actual fine-tuning work or actual model development. And so as models get better, Acceleragent just benefits from that. And if you happen to have a fine-tuned model with specialized knowledge, that should be usable by Acceleragent. But we've never fine-tuned a single model as part of this work. We just use kind of whatever latest frontier model we have access to. So, so I think one of the keys here to using AI is getting the right requirements to the AI at the right time. And so for HPC codes, especially, I think it's crucial that the AI doesn't own the definition of correctness, but that really belongs to the human users. So the AI has the code basically, and that's it. And so it can infer what the code should be doing, but it's not. I don't think it'll ever have the full picture. Like it's not going out and meeting with stakeholders, that sort of thing. Um, so the best way we found to make sure the AI doesn't go off the rails is to define what end-to-end correctness for the code base itself is at the user level. So that's the other input to Acceleragent is a set of scripts that build and run the code and return a zero exit code if it succeeds, and if anything fails, return some non-zero exit code and useful information about what went wrong. And so this is a place where I think it's crucial that the user thinks carefully about what correctness is and provides that to the AI and bounds the AI to work inside of that definition. Um, yeah. Okay, so I'll skip this for time. We talked about, yeah, so sort of briefly, I think Acceleragent, we found it requires pretty strong LLMs to do a good job. So it's kind of models with small numbers of parameters, open source models tend to not write great code that's not well aligned with itself across many steps. So we tend to favor frontier models for this. Like, I use the latest Claude Opus that's available. I haven't tried Fable yet, but I want to. But the LMs are improving rapidly. So in the 6 to 12 month time scale from now, I could see open models being good enough for this this kind of work. But our results so far say that it's really the closed source frontier models that do a good job on this specific tasking. And so Acceleragent doesn't really care which language you're going from and to, because we're sort of just asking the AI to write the code and read the code. So it's just a matter of asking it to translate Fortran to OpenACC or C to Kokkos. The bold arrow here could actually be Fortran to Kokkos, but we found generically the frontier models know a lot about all the major languages and accelerator frameworks. Okay, so let me give an example of using Acceleragent. So this is something I ran last week. So Miniweather is a 2D open source weather hydro code you can get online on GitHub. So I downloaded that. I prepared a special version of that repository with just the serial Fortran implementation. It comes with a lot of GPU implementations as well, but I didn't want to give the model any hints about what it should be porting, with the existing GPU implementations in the same folder. So I used Claude Code and had it use the project acceleration skill to port to Kokkos. So really all I did was navigate to that folder in my terminal, open Claude Code, and tell it use the acceleration skill to port this code to Kokkos. And the skill gives you some initial interview questions about what you want. So do I want it to use Nsight to do end-to-end profiling and read those profiles? Yes, I do. I wanted to port the entire code base rather than like some physics submodule. Miniweather is pretty small. It's actually just one file, 1,000 lines or so Fortran. So this is just a demo example. So I told it to use managed memory rather than explicit copies. And then I told it low user engagement. I just wanted to work as much as it can. So I hit enter on those, and Claude Code just ran for 90 minutes. And this is the result. So it ported 6 functions from Fortran to C++ to Kokkos with associated unit tests. These are the right functions to port. So it successfully captured all the data parallelism in Miniweather. So it moved about 800 lines around and wrote about 2,100 lines of code between new C++ and Kokkos code and unit tests. And this is about 800 million cache read tokens. So when agents run, they do some work for a particular turn, and then they call a tool or something and do more work. But they keep the context of what they've done previously, and it turns out you can cache that and read it for very cheaply. So 800 million tokens is not the same thing as like giving 800 million unique tokens to an API call. So this was about $100 of Claude Opus 4.8 tokens. And the result was the AI port of mini-weather was about 2.5 times faster end to end than all 72 Grace CPU cores. This is on a Grace Hopper node, and so as compared to the Fortran MPI OpenMP version. So this is a reasonable speed up, not great, and we haven't really seen optimal ports come out of Acceleragent. That's not really what we're asking the AI to do. We're saying, take the code, get it running at GPU, do a reasonable job, and then we'll take it from there and optimize in more detail what we want to later. And so I think, the 2.x speed up is comfortably where we want to be for that first pass. But I think the really interesting thing about this result is actually that where the AI spent most of its time. So writing GPU kernels is only like 20% of the actual effort here. Most of it is like instrumenting the code for profiling, writing unit tests, integrating back into the original code, fixing its own bugs. But there's a lot that goes into removing most of the work of an end-to-end port. There's a lot more than just rewriting kernels one at a time. I think to really get significant speed ups, you want the AI to be integrating those kernels into the original code and making sure the original code is correct. And this is a result that's sort of generic when we try porting codes. Is most of the work really is getting everything set up and working properly, and not just writing kernels. So here's another example. So mini-weather is a small code. This is MPSA is a production weather code, almost 500,000 lines. So this is just to show that the sort of project acceleration stuff works inside of larger code bases as well, because this code's way too big to just put into an LLM context window and ask for results out. So this is with the older Python command line version, but we had successful ways to navigate through a large code base, get the right context at the right time for each prompt, and port a targeted region. This is the kind of the fluid solver core of MPSA, kind of a 4,000 line region. Port that to OpenACC successfully without overwhelming the AI with the wrong context. And this is something coding agents could do pretty well too. They have their own tricks for managing context and using tools to find the right files they need to read. And so for MPSA, it ported 6 functions. Each function was sort of hundreds of lines. It contained many small kernels to port. So we saw kind of mediocre performance from the GPU port here. The human port from a more recent version of MPAS is typically a few times faster than the GPU version. And that mostly came down to the AI ported most, but not all of these data parallel regions to GPU. And so there's memory motion essentially that hurt performance a lot. But as a first pass, I think it got most of the code onto GPU correctly, and then the human can come back in and clean things up. So I'll conclude here because if there are questions, I want to leave time for that. But I think it's true now that AI models, especially agents, are really powerful tools for code porting in particular. I think the code porting problem is especially nice for AI because a code that works in one language is great context to writing the code that works in another language. So it's a good problem for giving the AI the tools it needs to do some problem. And AIs are not superhuman at planning ports, but they are superhuman at typing. And with code porting, there could be a lot of typing, and AIs could do that part really fast. But making sure the AI does that typing correctly bounded by production requirements is a key challenge that has kind of guided our work. And so the goals of this project were sort of demonstrate and quantify the value that AI can add to initial ports of large HPC codes, and kind of identify and share best practices for how to do this. So it's project acceleration itself is not like there's not a whole ton of special stuff inside of our work that's required to do any of this. I think anyone can sort of download Claude Code and kind of just follow this program I laid out, or do with their own related ideas and get fast code porting. I think end-to-end GPU porting time can be compressed significantly with AI, kind of independent of the target GPU framework. But then getting a truly optimized GPU code is not a problem that we've really targeted or solved. And so after initial ports, there still remains the traditional performance optimization work to make applications run really well on GPUs. And especially for algorithmic changes, that's, I think, the biggest gap today between what AIs can do and what they can't be trusted to do. So thanks for your attention.
Thanks, Ben, for a great talk. I have a bunch of questions, but let first participants to ask questions. Any questions from participants? Yeah, while waiting, let me ask one question. So in reality, the Fortran developers want to continue to develop the code in Fortran. Once they finish the porting, how do they manage or maintain their code and continue developing?
Yeah, so in our model, we leave the original CPU code, and there's an alternate code path for GPU codes kind of on top of that. And I think many developers don't like that. So there is an inline option now we have where the original code base will be modified to contain, say, Fortran with OpenACC constructs. The original CPU code actually gets copied into that unit test to be used only as a reference. So you could do that, or the user could go back and delete the original CPU code once we're done. But once you've correctly ported to GPU, at that point, I think it's less critical to keep the original CPU code around, and it's a developer choice whether they want to maintain that or maintain only a performance portable code path, for example.
Okay, thank you. Thibault?
Hi, hello. Thibaut Simic from Grenoble, France. I'm sorry if you hear a very loud boom, but there is a storm above my desk. So if you hear a very large boom, I'm probably still alive, but careful for you here.
Sounds good so far.
Great talk, thank you. So basically, I've been doing what you've presented, but I've been the human instead of the AI and been closer to the LLM. Porting BFT code to Kokkos, which is a Fortran orchestrated code. So as you said, porting code is great for LLM because one of the best things they can do is translation. So going from one language to another with a lot of in big DFT, there are also backends, pure CUDA backend, cycle backend. So it can get quite a lot of context. When running those kind of flow graph that you shown, also with the Claude Code, but maybe 6 months, 10 months ago, it had a tendency to switch the goals from having the test succeed instead of the initial goal, and then it will try to cheat on me by avoiding a problem so that the test pass and say, okay, I've succeeded in making the test pass. Have you encountered this kind of behavior? How did you challenge them in your deterministic approach or in your LLM-based skill approach?
So I saw lots of this when I first started this project with older models, and our original solution to this was just to keep those verification scripts kind of entirely out of the domain where the AI can edit them at all. So you define what it means to build and run the code, and if the script fails, it's the code base's fault and the AI needs to fix it. And it's not allowed to actually touch the verification scripts at all. So if a verification script is comparing to a gold file that's not in context, I think that's very difficult for the AI to hack. The challenge with that is it turned out to not be very flexible in all cases. So little details like some flags not getting passed to a verification script to turn on GPUs will kind of crash the command line program. So as the AI models get better and more reliable, we've given the AI more freedom to modify the verification scripts if it really needs to. And I haven't seen much reward hacking recently, but it is something to be careful of. And maybe there's a way to still have kind of gated checks against scripts that AI can't modify to make sure it hasn't done reward hacking. And we also regularly do git commits with the AI workflow. So if something goes off the rails at some point, you can sort of back up to where things are actually working and then proceed from there. But I think having some testing environment the AI cannot touch is ultimately a requirement.
Yeah, okay. Thank you.
Mhm.
Thank you. And there's a question from Ivan in chat, and there it's generating multiple working versions of the same code database and compare them for performance and other metrics in something you have worked on. Supposing you are working on the same programming languages for different versions, I wonder if doing something like this could reduce the cost of optimizing the algorithm after, or maybe it's just too expensive.
So I know other people are doing this. Sorry, was the question using multiple different AIs to do the same kernel port and then compare the results?
Yeah.
Let me. Okay, so we haven't tried doing multiple ports of the same code base. So I think having kind of multiple agents compete to port individual kernels makes a lot of sense. But for the whole code base, we tend to see pretty good reproducibility for the model. Like there's kind of a correct answer for which function should get ported. The details like some aberrant memory motion because one kernel didn't get ported. I think those are things that you can catch with tools and then send to the AI for subsequent fixing without having a swarm of agents competing to do that the right way. And swarms of competing agents does actually become expensive. So porting mini-weather cost $100. If we had 10 agents all doing it that compared the results, it'd be $1,000. That scale can I think become significant for large code bases. So we sort of haven't gone down that path as much, and we haven't felt that it's critical to get a useful first cut port out to do that.
Thank you. And
but
additional question?
But maybe that is for more open-ended tasks, like you say, like choosing the right algorithm to switch to use GPUs. That's a place where a swarm of AIs trying different things could be really successful and actually probably necessary. Okay, so I can read the chat. I can ask the next question. So how long do you take to develop this agent? So we spent about a year doing the original Python version. So that ended up being a pretty big Python code, sort of because we had to capture lots of edge cases and be robust against lots of different things we were seeing. So there would always be bugs to fix. Every new code required some architectural change. We're kind of implementing a whole coding agent harness as well. So there's a lot under the hood there. But the agent skill, I basically took that Python code, that we developed kind of over a year, including a number of like false starts, trying different workflows that weren't really great for AI porting. And I just took that whole Python code, gave it a cursor and said, write me an agent skill to guide an agent to do what this Python code is doing. And it kind of just did that. So I'd say moving from a Python development model to an agent skill development model sort of took the development time scale from like a year to like a month. And we're seeing that going forward too. Like if I have some significant new feature I want to add to the agent skill, it's really quite easy to just state that request to cursor and have it implement that in the skill for me. The skill development path is really fast for this kind of stuff. So unless there's strong requirements to be constructing the AI prompts yourselves and deconstructing them, working with AIs, I would say starting from skills is the best path to move quickly. Okay, the next question, how can we use your tool for GPU porting? So we want to share this tool. We've had a couple of false starts with getting a license, but I think we're close now to getting a license that lets us share kind of on a user by user basis the skill, where we could just send it to you. You can run it on whatever you want, and we just ask that you not share the skill itself. So that may be ready in a week or two. So if people are interested, you're welcome to contact me, and we can talk, because we're interested in sharing, what we're doing, because our interest is in helping people get on GPUs, and so working with the community together to use AI to do this, I think, is something that we're interested in.
Yeah,
Okay,
that's great.
Thibault, you
We
had
had
a
a
question?
question from Thibault. This might be a
Yeah,
final
so
question.
I think you mentioned it earlier a little bit when you talked about the AI could actually use profiling tools to see what's what and make decisions from that.
Mhm.
Did you manage to actually see him going from a naive parallel for Kokkos kernel and turning it into something smarter from a GPU optimization point of view, using more advanced, closer to architecture features of GPU programming, like using tiling and shared memory or stuff like this?
So I haven't seen much of that kernel level optimization, and that's not really what we're asking the tool for. So Nsight Systems really gives a program level view of what the GPU and the CPU are doing. So the CPU runs for a while on the timeline doing initialization stuff. Then you go to the GPU, and the GPU's, busy to some fraction of memory bandwidth, say. And then you go back to the CPU. So what the Nsight Systems tool we're using is really to make sure the GPU stays busy, that work isn't being done on the CPU, and make sure that there's not memory motion between CPU and GPU that's keeping the GPU from having work to do. So we have seen the AI does a good job of reading those timelines and filling in that white space. I'm forgetting the details of the most recent example, but we have seen cases where the GPU will do some initial port, say there's like a lot of unnecessary memory motion after each iteration of some loop. It'll go back in after it finds that in the timeline in Nsight Systems, remove that necessary memory motion, and then get 10, 100x performance boost just by sort of writing sensible program scale CUDA. I think you can use kernel profilers like Nsight Compute to do a similar thing at the kernel level, but that's not really something we've looked at. I think other people are looking at that, but that hasn't been our goal.
Okay, and I have another question. Now you've tested this tool with, we could say, probably the best LLM there is to do code about. Do you think it would be a good idea going forward, trying to test with less efficient, less good LLMs, maybe worrying that the true cost of the biggest LLM is hiding behind some bubble that we don't want to burst or deflate? But
Yeah, and there are reasons where you might want to, run the AI completely locally in some environment to port codes. So I check this every 6 months or so, because what I really want actually is like to be able to put like an N1X laptop in my backpack or something, and walk into some place and open my laptop up. I have a local model running, and it's smart enough to run this Acceleragent stuff and port some code that I is on whatever computer I connect to through USB. And so I tested this a month ago with Nemotron 3 Ultra, which is a pretty strong open model. I think it's 500 billion parameters. But unfortunately, that was sort of not good enough for Acceleragent work. So it did port the simple code that I gave it, like a toy 1D advection code, but it took about twice as long as a Claude Opus model, and the result was also not great. So Claude Opus writes really clean code with, it doesn't have linting errors in it really, and the Nemotron result would have like unused include statements, lots of little details like that through the code that would need to be cleaned up. So, I mean, you could potentially combine an open model like that with linters, and ask the model to clean up, its own lint issues as well. But that's not something we've explored. And I think really my strategy is to just wait for those open models to get a little bit better. And I think within a year, there are going to be open models that are kind of good enough to run Acceleragent and be used locally. I think that's sort of the end successful state of this work, is to not be tied to cloud API inference. But I think I don't have a solution that's quite there yet from my perspective.
Thank you for the answer. That's great, and it's kind of very promising approach. And finally, I hope and the Fortran developers can make it with your tool. So thanks a lot to everybody for joining. And our next tea time will take place at the middle of September. We will announce it. Thanks again for Ben for the really amazing talk, and we may have another one in the middle of September. So bye. Thanks everybody.
All right.
See you
Thanks again
next
for having
in
me. It's great to
September.
talk to everyone.
Great.
Bye.
Thanks a lot. Bye.